Hello. So here was one of the FRQ problems from the test. According to the 2020 United States Census, 10.2% of American adults identify as multiracial, or as two or more races. An opinion poll plans to conduct a random sample of 1,200 adults. The poll reported that 12% of those samples identified as multiracial. Calculate the probability that this would have happened, that you would have gotten that outcome. And does that answer give us reason to be suspicious about the poll? So we were imagining that you would tackle this as a sampling distribution kind of problem, but a lot of people thought to choose to think about it as a binomial distribution, and I think both are worthwhile. So let's kind of think through both sides of this. So remember the kind of picture of what does it mean to be a sampling distribution. So in this case, it's a sampling distribution of proportions because we're talking about what proportion of the population has a certain characteristic. So let's imagine the population. So here's the population with 10.2% of them saying yes and 89.8% of them saying no. So you could imagine drawing a sample of 1,200 adults randomly from this group, this very, very large group. And when you draw a sample, you could count in that sample what proportion of them said yes to being multiracial, and that's going to give you some proportion. Let's say it's 0.13, and then you could draw another sample, and you could look at the proportion that said yes to being multiracial, and this time let's say it's 0.09, and you could do it again and again and again, and over time you would build up this distribution, which is the sampling distribution of proportions. And the sampling distribution of proportions is going to be centered on the true population proportion. So this 10.2% here is the mean. And then the standard deviation, there was an equation which you could look up on your equation sheet. So the mean is 0.102. The standard deviation is the square root of p times q over n, where p is the probability of success, so that's 0.102. Q is the probability of failure, so that's 0.898. And n is the sample size, so that's 1,200. So let me break out my calculator. So that's about 0.00874. So what we want to calculate is we want to calculate the probability that our particular sample would have come out to be 12% multiracial or larger. Because anything larger also we would have considered to be unusual because it's potentially far above the mean. So this is the area that corresponds to the probability we're interested in. We're interested in probability that, well, here I've just written x. Later on we'll get into better notation. Really we're interested in p hat, because p hat is the proportion of our sample. But we're interested in the probability that that thing is greater than 12. So this is a great situation to use normal CDF because the central limit theorem ensures that the sampling distribution is approximately normal. So we've got a mean of 0.102, a standard deviation of 0.00874, a lower bound of 0.12, and an upper bound of infinity. So let me, again, break out my calculator. And I am getting 0.0197 approximately, which is about 1.97%. And that's pretty unlikely. So I would say that's unlikely enough that I have some reason to be suspicious about the polling procedure. So if you were going to write this down as your solution to an FRQ, remember you should write down the conditions that justify using a normal model for your sampling distribution. So the conditions are that the samples were drawn randomly, independent of each other, and that the sample size is greater than 30. So given those three, central limit theorem implies that the sampling distribution is approximately normal with these parameters, with a mean that's the same as the population proportion and with a standard deviation that's given by that equation. Okay, cool. So how would you think about this if you were thinking about it as a binomial distribution. So very similar. It's like we're imagining a population that has like hundreds of millions of people potentially. So it's just like a giant bag full of people. And as you reach into the bag and choose adults at random, one at a time, there's this fixed probability of 10.2% that the adult that you draw out of the bag is going to be multiracial. And so we're imagining drawing 1,200 people out of the bag. And the question is, what's the probability that a certain number of them are going to end up being multiracial? So let's think about it that way. The conditions that need to be true to use a binomial distribution as a model, we need to have Bernoulli trials. And if you remember Bernoulli trials, there is binary outcomes. So yes or no, multiracial. The probability of success is fixed. And as we've talked about before, it, strictly speaking, is changing a little bit every time you draw somebody. But the population size that we're drawing from is so much larger than our sample size that we will treat it as being constant. And then what else? Independent. Independent draws. Which again, strictly speaking, not true, but the population size is large enough that we are treating it as if it's true. All right, so this is what justifies a binomial distribution. And you can calculate the parameters for the binomial distribution. You could say, like, what's the mean and the standard deviation. But that's actually not relevant for us to do the probability calculation, at least not with our calculator. A couple of people decided to set up the probability calculation for what is the probability 12% of our sample would be multiracial. When we're working with a binomial distribution, we're not working with proportions, but actual numbers of people. So 12% of our sample of 1,200 people is 144 people. So you might wonder, what's the probability that exactly 144 of the 1,200 people we drew would have had this success condition of being multiracial? And so you could calculate this exactly using the binomial formula. So you'd have 1,200 choose 144, because 144 out of that many are multiracial, times the probability of each person being multiracial, but then there's 144 independent cases where that happened, times the probability that they're not, times whatever 1,200 minus 144 is, which is 1056. So you could calculate this probability, but let's imagine the binomial distribution for a second. I don't know if you remember, but when the sample sizes are very large, the binomial distribution can be approximated very closely by the normal distribution. So now, like, visualizing the situation, now it's maybe helpful to figure out what's the mean of the binomial distribution. It's just the sample size times the probability of success, and that will give you the expected number of successes. So for us, that's 1,200 times 10.2%. So that's 122.4 people. And remember, we actually saw in our poll that 144 people were multiracial. So here's 144. The probability that we calculated here is the probability that we would have gotten exactly 144. But we also would have been surprised if 145 had been multiracial, or 146, or 200, or 500. So when we're deciding if we have reason to be suspicious of the poll, we actually need the probability of the outcome that seemed like an extreme outcome, or anything that would be more extreme than that. Because all of these together are situations that would have caused us to pause and ask, is something unusual happening? And so we want to know the probability that any of those unusual situations would happen. So it might be, well, it's not true what I'm about to say, but let's pretend that this probability was like 1%, but the probability corresponding to any of these events was like 10%. That would be a case where 10% isn't so unlikely, so we would say we don't really have any reason to be suspicious of the poll, even though the probability of the particular outcome we got was very unlikely, 1%. All right, so because it's sort of unwieldy to calculate this probability by hand, that's when we'll use binomial CDF function. The binomial CDF function, what do you give it? Let's look. Okay, right, I'm remembering here. So trials, there were 1,200 trials. Our probability of success, our probability of success was 10.2%. The X value we're interested in is 144. Let's paste it. Okay, 98%, that seems very likely. So let's remember, like, what did this actually compute? We actually computed the probability of getting 144 or fewer. If we want to know the probability of 144 or greater, what we really want to do is find, so we want to know this, greater than or equal to 144. So that's going to be the complement of X being less than or equal to 143. So if you imagine shading in, let's do that in green. So this area is the probability of drawing 143 or fewer. And 1 minus that is all the other things that might happen. So it's 144 or greater. So this is actually the one that we want to compute. So let's go back and try it again. Distribution, go down here to binomial CDF. 1,200, 10, okay, but now I want 143. And I want 1 minus that. So we'll say 1 minus, and you can go to second answer down here. All right, so now we've got 2.4% approximately. So it's a different answer than we got on this side, but they're both pretty close. And the reason that they're different is because in this case, when you're using a sampling distribution, we're using a normal model to approximate the true sampling distribution. And whenever you have an approximation, you're not going to get exact probabilities. So this side over here, the binomial side, actually would give us an exact probability. But either approach would be fine, and both approaches are standard. And the sampling distribution approach was the one that we'd intended people do because that was a real emphasis this unit. Anyway, I hope that this has helped. Everything here is relevant. On the retakes, we might ask exactly this sort of thing where you have to realize it's a sampling distribution, write the conditions, figure out the mean and the standard deviation, and then use a normal model to compute a probability. Or we could equally well ask about this side, and same thing. You'd need to realize what the conditions were for the binomial distribution to apply. You'd need to realize that calculating a particular binomial probability may not be the exact thing that will help you answer the question if you want to know, should you be skeptical of a particular outcome. All right, I hope that this was helpful.